Okay. So we are going to go ahead and get started. I'll be covering the assignment for this worksheet 7.2 and worksheet 7.3, the graphing thing, and then we'll probably finish notes depending on how I'm feeling. Yes. Okay. So we're gonna start based on. So after you do the graphs, it should look a little something about like this. I just took a screenshot of what I did. So, and I deleted it. But yeah, should look a little something like this. It'll be a lot easier because you'll have the paper in front of you. Yeah. So let's get started. 7.2 asks, based on the data and your graphs, what can you conclude about the two chlorophylls and their absorption spectra? Oh, and I also forgot. We were supposed to look up visible light spectrums. I believe it was visible light spectrum. Let's look at the frequency because that's what we need. Right? Crap. Should have had this done before. Based on the data in your graphs, what can you conclude about the two chlorophylls and their absorption spectra? So, okay. So when we look at our graphs, we see that our wavelength for the two chlorophylls. So we're looking at the one that is not on 7.3. So we're only looking at, like, look at mine, chlorophyll A, chlorophyll B. I have this. That would explain that. There we go. Add it to the wrong thing. Oops. We look at this. It would be. Well, if we look at chlorophyll B, we see that between these two, between those are when it absorbs the most. So at 450, it absorbs the most, and we see that 450 is let's see. Okay. 1, 2, 3, 4, 5. Or wait, 1, 2, 4, 5. So it absorbs the most. Chlorophyll B just absorbs more blue, while now if we look at chlorophyll A, it will absorb. Let's see, that's about 25. I guess they both absorb about the same amount of blue. So it's more. Chloroform A and B both absorb a good amount of blue. But can you conclude about the two chloroforms and their absorption spectra? I mean, probably that they're blue, I would assume. But then they absorb more, so... I would assume that would mean that they... So, we can assume that it would be blue. Now, these are not the confirmed answers. She'll probably go over this in class. In which, oh well, you know what I mean. Okay, so chlorophylls are the predominant pigments in leaves. Based on the data and graphs, give a possible explanation for why plants are green. Am I looking at this wrong? Because I look at it 450. Actually, I think we can assume that they would be green as they absorb everything else except for green. That would be a better answer. Because we look at the electromagnetic spectrum, 500 to 600 would be all, you know, that stuff. And we look at our graph, from 500 to 600, chlorophyll B and chloroform A do not absorb a lot. They absorb everything else. And they're different because they differ in how they absorb, or in what intensity different colors are absorbed. Okay, so chlorophylls are green because they absorb every other color besides green, or they reflect green. There we go. Let me hang on. Zoom in a little bit more for this. There we go. If some wavelengths of light are absorbed by chlorophylls, what happens to the other wavelengths that are not absorbed? Well, they're probably reflected. The wavelengths are most likely reflected. If they're not absorbed, which explains something's color. Okay, explain why leaves are green. Leaves, because white light comes from the sun. This is going to be a very interesting answer. Because I have not thought about this. Oh. The white light is split in the atmosphere. Or no. White light is made out of everything. And white light is all the colors mixed together, meaning that if something reflects all the other colors, or if something absorbs all the other colors, then the color that is reflected into your eye will be the color not absorbed. If that kind of makes sense. So basically, it absorbs every single other color from the sun, and it reflects every other color, or the colors that are not absorbed. So like in the case of leaves, green. And that's what you see. Yeah. Based on the above data and your graph, which type of light is most important to plants for photosynthesis? Well, definitely 400 to, if we look at our graph, definitely 400 to 450. So, probably blue light, I would assume. Yeah. Yeah, I'd say light from the color light of the wavelength from 450 or 400 to, I'd just say 425. Wavelength of 425 as it is absorbed. That's what I would guess. Now give me 1 second to type all of these answers. All the worksheet 7.3. I didn't think that we'd get done this early. Oh, holy crap. You didn't hear that. Okay. So, what observations can you make about the similarities and differences? So, if we look at the graph, if you flip to it. Actually, if we just look at our graph, it absorbs, so the carotenoids, I don't think I said that right, absorb a lot more color, or show a lot more color and absorb, caps lock, and absorb less. Man, I just got a new keyboard. And if we just look at ours, well, if you look at the worksheet, like, the rate of photosynthesis, like, photosynthesis happens as well. Photosynthesis happens the more of happens as well. Photosynthesis happens in a similar manner to absorption. I spelled that right the first time. Now focus on the left half of the graphs. Notice that the photosynthesis graph has a wider peak than the chlorophyll absorption graphs. It doesn't bottom out until 500, 600 nm. What does this mean? This means that if we look at our electromagnetic spectrum, 500 to 600 is about green. So this means that green is not good for photosynthesis, which might explain why it is reflected. The action spectrum shows that photosynthesis occurs in light that is not absorbed by chlorophyll A or B. That is not absorbed by chlorophyll A or B. Propose an explanation for this. Let me think real hard. photosynthesis does occur, but it's not at a huge rate. That's what I would assume the answer would be. But let's Google it. That didn't really help. Oh, Jesus. Get that done. Let's see. I would just say, just because it is bad for absorption does not mean that photosynthesis does not happen. A very small amount could still be absorbed. Yeah. Man, how could you collect evidence to support your hypothesis? Man, did I just not type out all of these? I did not. I'll have to go retype these. How could you collect the evidence to support your hypothesis? You could, in theory, subject plants to green light and see how they react. That is what I would say, because how they react compared to no light. Because if they live longer in green, then some photosynthesis does happen. Alright, well, let me go retype these answers real quick. We only got 6 left. We're so close. Okay, let's get started. Analysis. By looking at your graph, explain why the action spectrum for photosynthesis shows wider activity than the absorption spectra. So what this is saying is, why is photosynthesis higher than? And we're looking at, like, for mine, it would be the red part. Why is that higher, or why is the photosynthesis higher in page 1 for 7.3 than the absorption? Than the absorption spectra for the chlorophylls. Okay. For the chlorophylls, sorry, we're not looking at the red. Why do the... Probably because photosynthesis is always going to... Photosynthesis is always occurring while absorption is happening way less. What color are carotenoids? Well, they down at 550 to about 650. So if we look 550 to 650, or is it 550? Yeah. 550 to about 650. We'd say about orange. So they are orange as their spectrum is 550 to 650. About. What is the adaptive value of accessory pigments like carotenoids? What advantage do they provide to plants? I would literally just assume they... I don't know. She said we're allowed to Google. That makes sense. So during during fall or spring, the plant can still absorb light and continue photosynthesis. They provide almost year-long lifespans. So basically, like, carotenoids allow like leaves and plants to turn orange in the fall and spring. Or during fall. I don't know what I'm talking about. That way they can still, live. That might be a little important. Leaves of trees in many parts of North America change color in the fall or before dry station. Because... Did I not type number 2? I did. Because the light is... I would assume... carotenoids allow more light to be absorbed during the fall when there is less sunshine. That is what I would assume. Because we go from this to like... We go from stopping at this to starting at this and going all the way here, which is a much wider spectrum. What is a beta carotene? We're about to figure out. Found in plants that give them their color. An organic, strongly colored red-orange pigment. So a beta carotene is a strong red-orange pigment in food. It is found in plants to give them the color. What does it do for plants? All right, it converts in, we see right here, beta carotene converts into vitamin A. So beta carotene converts into vitamin A, which is good for eyes and other things in the human body. What does it do for plants? Let's see. It allows, I would say, they absorb more. I would just put they absorb more light. They allow more light to be absorbed for plants. And then, guess what? We're done. That is all that was on today's assignment. And now I don't think I'm going to do the notes. Simply because I don't feel like doing it. It is 11:15 right now. Yeah, I got off of work an hour. So I think that's enough studying for tonight. You have any questions or anything in biology, you can talk to me, Yeah. Okay. Bye-bye.